Let's talk about our first class in our phylum Arthropod called class Crustacea. Class Crustacea are our chitinous exoskeleton group. They have two pairs of antennae, which you can see on our animal in the picture on the right. You can see there's one pair of long antennae pointing to the back and two pointing forward. They have mandibles, which are jaws that are used in order to crush food. They have one pair of compound eyes. You can see in this picture. Here as well, and here. They breathe through gills, and they have an exoskeleton, which is a hard outer skeleton.
The mantis shrimp is a true heavy hitter. Take this one. She's about to devour this snail, but she's got to crack it open first. So she carefully positions it. Then, bam! She punches it with the speed of a .22 caliber bullet. It's the fastest attack in the animal kingdom. That's one kind of mantis shrimp, known as a smasher. Here's the other. This one's called a spearer. Buried up to his eyeballs, he watches and waits. Then, springs into action, impaling his prey on a serrated blade with blinding speed and dragging it beneath the sand. What makes these two so amazing isn't just their speed, it's their eyes. See those black spots? They're like our pupils, where the light enters the eye. We humans have one in each eye. Each sends an image to the brain, and voila, depth perception. The mantis shrimp has 6 of them. Our vision, binocular. His vision, hexnocular. For when accuracy counts. As for color, we've got 3 receptors, red, green, blue. The shrimp has 12, another world record. But there's even more to this incredible eye, and it has to do with something called polarized light. Sunlight is messy. It's a jumble of wavelengths moving in all directions at once. But some surfaces, say the scale of a fish or a pair of polarized sunglasses, have a way of changing the light, organizing it so it moves in a single plane. We humans can't really tell this is happening, but the mantis shrimp can make out where in the ocean light is being polarized and where it isn't. Some mantis shrimp take this one step further and produce their own special kind of polarization, and they use it as a secret code. See, mantis shrimp are incredibly territorial. They will defend a burrow to the death. But some, like our smasher, have a way of avoiding the fight. When he looks into a burrow, he can tell that another mantis shrimp has already claimed it by the way light is hitting its body. That's the secret code. Here's how it works. Remember when I said that polarized surfaces organize light into a plane? Well, these surfaces on the mantis shrimp make the beams of light circular, spinning through space like a helix. As far as we know, only other mantis shrimp can detect this with their eyes. You can see it here because we put a polarizer on the camera. So these shrimp have taught us a thing or two. By reverse engineering the mantis shrimp's eye into a camera, a group of scientists have begun to use polarized light to diagnose injuries and disease. This scanner measures polarization in red. See how this mouse tissue goes red when it stretches? Well, injuries to our tendons do the same under the scanner. So do some cancers. This endoscopy footage reveals cancerous cells hiding in plain sight by the way they react to polarized light. It just goes to show how we see the world differently when we look at it through another set of eyes. Hi, it's...
Pretty cool, right? All right, continuing. Most crustaceans are free-living, but some are sessile and some are even parasitic, meaning they live inside another animal, feeding off what they're living in. We've watched this video before, so I'm not going to show it again, but you can see how the isopod actually goes into the fish mouth and lives in the mouth as the tongue, eating the fish. Some crustaceans reproduce sexually. Some are hermaphrodites, like we talked about the barnacle in our last video. Here's a super fun fact. The Japanese spider crab is the largest crab ever recorded. And look how big that crab is compared to that full-grown man. It is a whopping 26 feet long. Some examples of crustaceans include lobsters, crabs, shrimp, and crayfish. Here's a video for you looking at the amazing shell exchange between crabs.
Hermit crabs use abandoned seashells as mobile homes. As a crab grows, its shell becomes an ever tighter fit. So eventually a crab needs to move in to a bigger one. Suitable empty shells are few and far between. And this one is far too spacious for this crab. But instead of continuing its search, this small crab settles down to wait. Other crabs, also looking to upgrade to a bigger home, soon gather whenever a shell washes ashore. Unfortunately, the new shell is too big for them too. Despite that, the gathering crabs begin to measure each other up, and then they do something really rather extraordinary. They arrange themselves into an orderly queue. The biggest at the front, smallest at the back. They're lining up with one aim: to exchange properties. But none of the crabs can make a move because the chain is not yet complete. They're all waiting for the right-sized crab to come along. And this is it. The latest arrival pushes to the head of the queue. At first, the chain falls apart. As it reforms, the small crab finally makes its move and takes its place at the end of the line. After a close inspection, the big crab moves in. This triggers a chain reaction. Each crab hurriedly moves into the shell vacated by the crab ahead of it in the line. Just as the small crab attempts to move into its new home, a fresh arrival muscles in. To be left without a shell is a death sentence. A naked crab will quickly cook under the intense tropical sun. But after all the swapping, there is still one shell left. Sadly, it's no bigger than this small crab's original shell. And worse, it's got a hole in it. But even a bad shell is better than being homeless.
chaotic, turbulent, harsh. The ocean's edge isn't the easiest place to make a home. And yet, someone does. Pacific mole crabs, also called sand crabs. You've probably seen the little holes they make. They spend their lives just under the surface of the sand, waves crashing overhead. That ever-present flux offers a meal. Each wave kicks up plankton and other tasty morsels. They peep out from below the sand and use their feathery antennae to catch food right out of the water. But they can't just sit around gorging themselves all day. The crabs want to stay in the swash zone. This part here, where the waves break and sweep in. But it's always moving with the tides, up and down the beach. So the mole crabs have to move with it. But they're not the only ones out here looking for a meal. To birds, they're basically beach candy. Easy pickings. So mole crabs have become champion diggers. They can disappear in a flash, back under the sand to hide. But they have to be fast. So what makes them so good at burrowing? Researchers at UC Berkeley want to find out. Back at the lab, they filmed the mole crabs in action using high-speed cameras. Mole crabs actually burrow backwards, digging into the sand with their pointy rumps. But moving densely packed sand is hard work. The grains stick to each other, making it tough to push through. So the crabs have become tiny engineers. They stir up the wet sand with their tails, making it easier to move. A process called liquefaction. Then they push the loose sand up toward the surface by handing it off between their 5 pairs of legs. See? Kind of like a conveyor belt. The waves never rest. So the mole crabs do this day and night as they're tossed and tumbled. But they take it all in stride. When you survive on chaos, fluidity is what it's all about. Hi there, it's Lauren again. Make sure not...
There is one more video I would like you to watch called Shape of Life Marine Arthropods, but I'm going to link this one into Schoology. All right, after you've watched that, that's all we have for Class Crustacea.